Hi, guys. You wonderful earth science students are going to get to learn about rocks and minerals now. So we're going to start out with minerals. That's because minerals get together to form rocks. So a mineral is a naturally occurring inorganic substance of definite chemical composition and physical characteristics. So, number one, it's naturally occurring. It has to occur in nature, not necessarily at all man made. Now, we may be able to make some of the minerals, but the original mineral has to be something that could occur in nature. Inorganic substance, in other words, not made by living creature. Technically, a kidney stone is not a mineral. Has to have definite chemical composition. Think of, for example, water, H2O. That's a definite chemical composition. There's H2, that means two atoms of hydrogen, O, one atom of oxygen. So that would be a definite chemical composition. And definite physical characteristics. In other words, each mineral has its own unique characteristics. Okay. So a mineral is special because its atoms are arranged in a perfect grid. The atoms have a basic pattern that's repeated over and over. If we were to play Magic School Bus and become super tiny and fly around and maybe go through this apple, we would find that it's a mess. There's nothing clear and defined about it. But if we were to go through a mineral, what we would find is that as soon as we were in it, the atoms would be laid out in this perfect grid, as far as the eye could see, just this pattern that continues over and over. So only things that are in crystalline form are like that. But all minerals basically are in crystalline form. So that's one of the reasons why a mineral is special. So a mineral is just the atom's way of satisfying all their electronic needs. What are the electronic needs of an atom? Well, there are two major electronic needs of any atom. Any atom needs to have its charges balanced. In other words, it has as many protons as electrons. That means its charges are balanced. Otherwise, it has a charge and it would like to either get or lose an electron. The other thing about them is that they would like to have their outer shells filled. Now, these two rules cause the elements to combine in certain ways to satisfy those two electronic needs. The study of that is called chemistry. So where are all these atoms coming from? All right, well, all of the Earth's atoms come from the cloud of gas and dust that formed the sun and the solar system. The atoms were originally created inside stars from lighter elements. So while they may have gotten together in the Earth's crust, that's not obviously where they're from. They are from outer space. And how did they get there? The universe formed and was just hydrogen inside stars. The reason stars glow is because they're putting elements together, making heavier and heavier elements from hydrogen. And the periodic table of elements is basically made inside stars. And when stars explode, they cast those enriched guts out into space. And when solar systems form now in the universe, those enriched guts can be incorporated into the solar system. When you look around, hydrogen might still be the most common atom around, but we have lots of other atoms, and every one of those atoms can have only formed inside stars. So why are some atoms more common than others? Well, some stars make large amounts of certain elements. These elements are therefore very common throughout our galaxy and will be found in most Earth substances. Of the Earth substances in our crust, oxygen and silicon are by far the most common types of atoms in the Earth's crust. So if oxygen and silicon are so very common in Earth's crust, if there's some way that we can bind them all together and electronically satisfy all the atom's needs, this would be a very, very common molecule on Earth's crust. And it turns out that we have something called the silicon-oxygen tetrahedron. Now, if you take a look at this, the big circle, the white thing here, represents the oxygen. They're very, very large atoms. And the black circle represents the silicon atom, a much smaller atom. And if we take three more atoms and we put them together in such a way so that the silicon atom is at the center of it, we would have something known as that silicon-oxygen tetrahedron. And the tetrahedron, being triangular on all sides, is an extremely stable structure. So of all the minerals, this one is probably the most stable on the Earth's surface. It's just very hard to break it down. Chemically or physically, you can't bust this up too easily at all. So what's based on that? Take a look at that. One of the most common minerals on the planet Earth is quartz. Everybody knows about quartz. Beach sand is made of it. How durable is beach sand? Think about how the waves are always smacking it. Salt water can be very corrosive towards a lot of things. Constantly smacking and beating it for millions of years. Does the sand really break down very much? No. The reason it's there is because it'll only break down so far, and then it's carried out by the rivers and gets deposited all along the seashore. So quartz, just based on this silicon-oxygen tetrahedron, is an extraordinarily durable mineral. So in terms of the silicon-oxygen tetrahedron, take a look at this. If we have a single tetrahedron, it forms the mineral olivine, or it could form quartz, very handy. But if you get longer chains, you could form the mineral pyroxene. If you get double chains, okay, you can form the mineral amphibole. All right, but look at this. We're getting increasingly more complex all the time. With a sheet of it, you could form micas. Then with a big three-dimensional network, you could form feldspar and quartz, right? But those require the big three-dimensional networks of all of these things put together. Well, if we think of what heat is, what a warm atom is versus a cold atom, a warm atom is simply vibrating faster. A cold atom is vibrating very, very slowly. That's what heat is. So if you think about the Earth's interior as obviously a very hot place, when would these atoms be able to form? At really high temperatures. Would you be able to form the more complex ones? No, they would be shaken apart. At really high temperatures, turns out you can form the really simple ones, like olivine. At lower temperatures, you could form the progressively more and more complicated ones. So the structure of SiO2 makes a lot of sense in terms of when these different elements would form. Is SiO2 going to be really important? Of course, because that's the most common element in Earth's crust. So anytime you have a liquid part of Earth's crust, you're going to have a lot of silicon and oxygen to deal with to form into various minerals. So obviously many, many minerals use that as their basic structure. So minerals might be elements, which would be only one type of atom, all put together for gold and silver, for example. Or they might be compounds, specific combinations of atoms, like quartz, SiO2, or calcite, CaCO3, a very important mineral. And they might be varying amounts of atoms. For example, feldspar. So here we would have the feldspar. What a beautiful mineral. No, it's not. It's not really that pretty at all. That's why even though it's the most common mineral on the planet, not too many people have even heard of feldspar. It doesn't make those pretty crystals like quartz does. Quartz is second most common, but feldspar is the most common because that's an aluminosilicate. Remember, the third most common element in Earth's crust is aluminum. There's a lot of it. So if you have a particular molecule that can soak up not only silicon and oxygen, but aluminum as well, that's going to be really common. Aluminum will pick up, feldspar will pick up sodium, potassium, or calcium as well, and it can use those in different mixtures. Those are really common as well. So this is a mineral that will use up a lot of the elements you normally find in Earth's crust. Most common element, most common mineral there is, feldspar. So a typical rock will be formed from one or more minerals. If it's made from one mineral, it's monomineralic, mono meaning one. If it's made from more than one mineral, it would be called polymineralic. So some minerals or some rocks just have one mineral in them. Other rocks are filled with different minerals in them. So how many minerals do you really need to know? Well, there are over 4,000 minerals identified so far, and there are more being discovered every month on our great planet Earth. But most are very rare and very difficult to find. Here's a nice one to find. If you could find some gold, that's pretty handy. Um, Gold would be monomineralic. There's just one mineral in there. But you can see this rock here has gold in association with with other minerals, and so that would be polymineralic. So you can have monomineralic or polymineralic. So what do we really need? Well, there might be 4,000 minerals, but if you know the 12 most common minerals, that will allow you to identify almost every rock and mineral you will ever see. Somewhere around 12, and you now know enough minerals that you sound really smart in terms of the minerals you find every day. So in terms of properties of minerals, this is pretty neat. Each mineral has very specific properties that will enable us to identify it. These properties are due to the way the atoms are bound to each other in the mineral. The internal arrangement of atoms determines pretty much everything that goes on in a mineral. So why do they have these certain properties? Just told you. It's that internal arrangement of atoms. The way that works determines just exactly what a mineral is going to not only look like, but it'll determine its behavior as well, whether it's hard or soft, its luster, it's all the different characteristics are determined by the internal arrangement of atoms. For example, two minerals could not be more different. Graphite, we use that in pencils. If you have graphite inside a pencil, you can write on paper. Why does graphite write on paper? Well, which is harder, the graphite or the paper? I'll give you a hint. If the graphite was harder than the paper, it would tear the paper when you try to write on it. But instead, the graphite just flakes right off on the paper, leaves a streak on the paper, because the graphite is much softer than paper. So graphite must be made out of a really soft atom. On the other hand, here we have a diamond. Diamond is harder than every other substance. It'll scratch every other substance. So diamond must be made out of a really hard atom. Well, the chemical formula for graphite is C. And the chemical formula for diamond is C. They're made out of exactly the same element. So what's going on here? How can carbon be soft in one place and hard in another? Because carbon is neither hard nor soft. Everything has to do with the way the carbon atoms are bound. Now, in class, I always tell about the Norwegian fisherman grip story when somebody is washed overboard from my grandfather's fishing boat, and in the freezing cold water, you will perish momentarily if somebody doesn't pull you back on board. Well, if somebody reaches down to grab you, you will grab their hand like this, and your two strong arms like this will pull you back aboard without fail. This is the Norwegian fisherman grip. Now, tell me, which one of these which one of these minerals seems like it's using the Norwegian fisherman grip? In other words, an incredibly strong bond that can't easily ever be broken. I hope you said diamond. Well, on the other hand, we might have what we would call the French fisherman grip, which is grip for much more temperate waters, and we're not that concerned if you don't pull somebody right on board the first time. So this might be the French fisherman grip, and you might lose that grip because it's not really that solid to begin with. Well, how about graphite? Is that using the more gentle grip? Absolutely. And that's the only difference between them. Made of the same stuff, but obviously bound very, very differently. So how could two minerals with the same composition be so different? Different internal arrangement of atoms. That's all. So that internal arrangement of atoms controls most physical properties. Pretty cool. So let's look at some major properties. Color is what it looks like to our eyes, but it's not always generally that useful because minerals can be in a lot of different colors. Luster is how the surface reflects light. And what you have to do is be able to determine, does it look like a metal or does it not look like a metal? And it doesn't even take much practice to be pretty good at that. When we streak a mineral, we rub the mineral, a point of the mineral, against an unglazed porcelain plate, and some of the color, some of the powder of the mineral comes off, and you can look at the color of that powder. Again, for as far as you need to know, it either looks like it's a darker color or it looks colorless or white. You can imagine if the mineral is harder than the streak plate, it's actually gouging up the streak plate. Hardness is how resistant it is to scratching. Will one piece of mineral scratch another? In practice, we just really want to know, will it scratch glass? If it'll scratch glass, it's harder than glass. There's at least one or two cases where you might want to try scratching the mineral with your fingernail. And if your fingernail will scratch it, you know your fingernail has a hardness of 2.5, so it must be softer than 2.5. Gypsum is a good one to scratch with your fingernail. Cleavage is breaking along flat surfaces. So if a mineral tends to break on flat surfaces, it has cleavage. If it doesn't seem to break along any flat surfaces, it has fracture. And density is how closely packed the atoms are. There are a few minerals that are unusually dense. Galena, for example. You put galena in your hands, man, that is really dense. Crystal shape is not very useful because crystals actually need space to grow in, and underground where you have minerals forming, there's rarely room for crystals to grow. So you don't see them too often unless you're in caves. Color can be, well, sometimes pretty useful. For example, this, if you could get a good look at that, that is sulfur. There's no other mineral that quite looks like sulfur. So sometimes the color is a wonderful identifier. But if you look at these two minerals, these are exactly the same mineral. So sometimes color is completely useless to use to identify minerals. Some minerals that are useful, this is mica. You could tell by its cleavage. It cleaves perfectly in one direction. This is also mica. How would you tell them apart? Well, this is the dark-colored biotite mica. This is the light-colored muscovite mica. So that would be an example where color is useful. There's no mineral that looks quite like this. This is pyrite, that brass yellow color. But one of the places where you find color to be kind of goofy, this is amethyst. Now, amethyst is really a variety of quartz. It's purple. How is it different from regular quartz? It's not really different from regular quartz, except the addition of incredibly tiny amounts of iron or some other like transition metals can turn it purple. So the tiniest bit of impurities very often will color something, and that's not really important to the actual mineral itself. So color very often is not a very useful quantity or quality about minerals. Many minerals have such a wide variety of colors. So there you can see that sulfur, right? That is a distinctive color. And look at the pyrite. Also a very distinctive color. Pyrite, as far as I know, pretty much always looks like that. Sulfur looks like that yellowish stuff. Now talking about luster, luster is the way light is reflected off a freshly broken surface of a mineral. So there's really two kinds of lusters, metallic or non-metallic. Give you a hint. Metallic lusters look like a metal. Non-metallic lusters don't. It's really as simple as that. Now there's some things that, it's hard to tell that it really looks metallic, but if it looks more like a metal than not, most of the time you're going to say it's a metallic luster. This is one that could be sometimes confused, but you can tell that does not look like a metal. These would both be metallic lusters. I think you can see even in the camera that Yeah, they look like a metal. They shine, they reflect light off like a metal. Non-metallic lusters. All right. So luster is pretty easy. There's that galena. That's the sample I was just showing you. It's this. Yeah, galena is beautiful. It always has that bluish silver color, and it looks metallic. Calcite. This would be a sample of calcite, and absolutely non-metallic. Hardness. Hardness is simply the resistance to being scratched. Which are harder, your fingernails or your face? It doesn't take a lot of thought to realize that your fingernails could scratch your face. So your fingernails must be harder than your face. Which is harder, your fingernails or this mineral? Well, it turns out this is one of the few minerals my fingernail can actually scratch. So your fingernails must be harder than this mineral. So we have a scale from 1 to 10 called the Mohs hardness scale, and we use that and assign all the minerals a particular hardness. Talc is the softest mineral. We turn it into talcum powder, like baby powder. Talc is the softest. Diamond is the hardest. So talc is 1, diamond is 10. All the minerals fall somewhere onto that scale. So it's a measure of how tightly the atoms in a mineral are bound together. Has nothing to do with the atoms themselves. For example, graphite. Let me grab some graphite for you. Graphite, this mineral here, is the same mineral or the same element that diamond is made out of. Graphite is so soft, it writes on paper. It's softer than the paper. But you take that same element, carbon, and you put it together a different way, so it's bound much tighter together, and you have diamond. So graphite goes from carbon goes from one of the softest minerals in graphite to the hardest mineral as a diamond. So the test for hardness is just to try to see which scratches the other. One object scratches another, it is harder than it. So you have the Mohs hardness scale. Talc, softest, diamond is hardest. So here we see the Mohs hardness scale, and you could clearly see, I think, that your fingernail comes in at 2.5, so it'll scratch that gypsum. It'll also scratch talc. Talc, when it's scratched, the little particles that fall down, pull them up between your fingers, and it'll feel a lot like baby powder. The big thing we use is glass. Glass has a hardness of 5.5, so anything down this way is softer than it. Anything this way is harder than it. And that's about what you need for the hardness scale. Streak is the color of a mineral's powder. So a streak is made by rubbing the mineral over an unglazed ceramic tile. If the mineral is not as hard the tile, some of the mineral will rub off. For example, if I take some of this galena and I rub it on this, you could see it makes a streak down the streak plate. Now, you're not supposed to rub it on this. Let me show you how you're supposed to do that, okay? Stand back over here, all right? You take the streak plate here, you have it on the table, so you're not going to cut your hands when you're doing it. You take the sample, you find a edge of the sample, and you pull it towards you, and that's all. That little mark there, you could say, yes, that mineral left a streak. That's all we're asking. Now, every streak is a little different color, but they're all some version of dark colored, so we're not asking anymore, did it leave a streak or not? Look at that. Look at that. Hematite will always leave a red streak. If I show you this, now this does not look like it would leave a red streak, but when I streak it, well, you can't see that particularly well, but that's the same kind of streak. This is actually a piece of hematite. Hematite and magnetite are fairly similar. The color of the powder can easily be seen against the white tile. If the mineral is harder, there'll be a white streak because it's just gouging the tile. Some metallic minerals have a different color streak than the color of a mineral. So the streak is useful because it's always the same color. So just like I showed, rub the sample on the streak plate. Don't do it in a way that'll hurt your hand. Sort of like with the hardness, don't ever hold a glass plate while you're doing a hardness test on it because they break. We like streak because it's extremely reliable. Every mineral always has the same color of streak. Crystal faces are really pretty, but where do crystal faces form? Sort of like this amethyst, it only forms inside a cave. So how common would that be? Right, not common at all. It'll only happen if a mineral is allowed to grow without bumping into anything. So it'll grow in very specific ways that represent its basic, what's that? Internal arrangement of atoms. It's a really important concept. The internal arrangement of atoms determines everything in a mineral. Pretty, lovely crystals of galena. Can you imagine walking into a cave and not knowing anything about minerals and seeing that? How did those cubes get there? So galena crystals are cubes because the atoms arrange themselves that way. So if you think about that and this mineral halite, which also forms cubes, they must have very similar internal arrangements of atoms, even though they're made out of entirely different things. So we can use the angles the crystal faces meet at to identify the crystals. But again, you would need an actual crystal, and those are rare. Cleavage is the tendency to break along lines of weakness. So if a mineral breaks along flat surfaces, like look at this, breaks along these beautiful flat surfaces, if a mineral does that, whoosh, right, it's said to have cleavage. Now, a lot of these minerals, if I smash this with a hammer, it's going to make a bunch of little rhombs like that. This too, calcite. I cannot break it, so it'll be nice cubes. It'll always be little rhombs. A rhomb is, you can think of it as a cube that somebody sat on and it bent. So galena will always break into cubic things. Halite breaks into cubes. So a lot of these have cleavage. They will break along lines of weakness. Here's a classic one. This is quartz. Quartz is an incredibly durable mineral. We talked about it. It's that SiO2, where your silica tetrahedron bound to that silica atom deep in the center, that silica tetrahedron, but it's equally bound really tight in all directions. So when you hit it and break it, you don't get any flat cleavage planes because it doesn't have a way that it prefers to break. It doesn't like breaking in all of the directions. So the surfaces may or may not be parallel to the planes of the crystal facies. Look at that. What kind of mineral is that? That's this stuff, biotite mica, right? Perfect cleavage in one direction. Perfect cleavage in one direction, parallel to the crystal faces. So here are some actual crystals of halite that would have grown in a cave. And if you look at them, they look a lot like the actual halite after it's been broken. So the natural crystals form cubes, just like it will cleave into. So if I smash halite with a hammer, it's cubes. And if I smash those cubes with a hammer and make it dust, I might need a microscope to look at it, but sure enough, they are still little cubes, even as tiny microscopic particles. Conchoidal fracture is a type of fracture. It's not a cleavage at all, but it's a tendency to break in these funny ways. And if you could just see this in the light, you could kind of see these semicircles here in the way it broke, and you could see some more semicircles here and there throughout the surface of this. This is actually a chunk of obsidian blown out of a volcano, smashed into the ground. On its way through the air, it already cooled, and so it just breaks when it hits the ground. This came to me from Hawaii, and it's filled with these funny curved surfaces. All right, so that would be obsidian These curved surfaces are called conchoidal fracture. And I like to use this term to show you that science terms are really not often as hard as you think they are. What does conchoidal mean? Well, if this is a conch shell, the way it has the way it looks, conchoidal means conch-like, so like a conch shell. So conchoidal sounds like a big crazy word. It's really not all that hard. So density and specific gravity. Density is a measure of how tightly packed a substance's atoms are, how squished together they are. Specific gravity is just a ratio of density of a substance to the density of water. Well, why are we using water? Check it out. Water has a density of 1 gram per cubic centimeter. Galena, very dense, has a density of 7.5 grams per cubic centimeter. So when we compare them for specific gravity, you don't need the units. So galena has a specific gravity of 7.5. You can see that's kind of makes it a little bit easier to talk about. So most rocks have a specific gravity of 2.5 to 3.5. Means their density is between 2.5 and 3.5 grams per cubic centimeter. That would be a typical rock you find on planet Earth. If you find one that is more dense, you would notice it as being extra dense. If you find one being less dense than that, you would probably notice it as being less dense. Look at lead. 12. Lead feels extremely dense. But gold is 19. It's about as dense as a substance gets. It is freakishly dense. When you pick up a lump of gold, you could tell that is more dense than almost anything else you've ever held. So let's talk about some special properties of minerals. Magnetism, like we already suggested, some minerals attract and hold on to magnets, right? So that would be a special property. A lot of minerals have a lot of interesting properties. Double refraction. Now, I can't really show that to you, but if you had a piece of really clear calcite, and this will only work with calcite, and really confused physicists for a long time that how did this work? And if you take a piece of paper and put a dot on it, you put the calcite right over the paper, as you rotate it, you'll see 2 dots, and one will stay still, and the other dot will go around it as you rotate the piece of calcite. That's bizarre. Calcite will also react with hydrochloric acid. In the geology lab, we usually have a bottle of very, very weak hydrochloric acid. If you got some on your fingers, you wash your fingers off. It's not going to burn or anything. But when you put that on calcite, you'll see it start to fizz. Again, you can't really see it well with the camera here, but you'd see it fizz a little bit. And that lets you know that the sample you have has some calcite in it. A really neat one that I want to show you. Some minerals will fluoresce under ultraviolet light. So I have some minerals here, and I have a ultraviolet light here, and I don't know if you'll be able to see that. No, I don't think that'll work out very well for you. Well, if you see some of these minerals seriously change color under ultraviolet light. I don't think I could show it to you like that. But trust me on this one. Some minerals under ultraviolet light are really cool, but really quite rare. That's not a common thing at all. So ultraviolet light, it's not useful for determining the mineral generally, but it is pretty interesting to see how that works. So identifying. Galena can be identified by its high density and its cubic cleavage. When you see a chunk of galena, you'll find it's pushing down in your hand very hard. That's galena. There's nothing else that's going to be like it. Quartz can be identified by its luster, its lack of any cleavage, and that it'll scratch glass. It's always hard. Mica, you can always identify mica by its cleavage, by the ability to just peel off these thin sheets that feel very plasticky. That's mica. Sulfur, no question about sulfur, can always be identified by its color. Magnetite is magnetic. And calcite will always fizz when hydrochloric acid is dropped onto it. So you have these certain these special characteristics that you can use to be absolutely sure of certain mineral identifications once you start learning the suite of minerals. And again, there's only 12 or a few more minerals to really know, and you know so many of the minerals around you day to day.